To demonstrate another use of logarithms, I'd like to consider the following function. This is y equals x cubed times the square root of 2x plus 1, all divided by x squared plus 4 raised to the 6th power. Now, taking a look at it in its current form, I would start with the quotient rule, then product rule for the numerator, power and chain rules for the denominator, another power and chain rule for this radical. Oh my gosh, I'm making myself sweaty just thinking about it. This is terrible. Well, there is an alternative, and we're going to look into this alternative. This is a technique that's referred to as logarithmic. Logarithmic differentiation. The technique of logarithmic differentiation is recommended for a problem like this and required for another kind of problem. So this will be recommended anytime your function is a large combination of products, quotients, and powers. In this case, we're starting with a quotient. We have a product in the numerator, and we have powers on all three of the factors that are here. This will be required anytime you have a variable to a variable power. We'll investigate that one next. So logarithmic differentiation is a variety of implicit differentiation. What I'm going to do is give the directions in red and then actually execute them in blue. So first thing we're going to do is take a natural log of both sides of your equation. So on the left-hand side, we would get simply the natural log of y, and on the right-hand side we would get the natural log of this very large combination of products, quotients, and powers. This function is now technically implicitly defined because we don't have y by itself on one side of the equation. We now have the natural log of y on one side of the equation. So step 2. Expand the logarithm as much as possible. Now for that, we'll be starting with the quotient property and call this the natural log of the numerator minus the natural log of the denominator. Then we'll apply the product property to the first natural log. Call this the natural log of x cubed plus the natural log of the square root of 2x plus 1. We'll call that a 1/2 power though, minus the natural log of x squared plus 4 raised to the 6th power. And finally we'll apply the power property to all three of these. This will be 3 times the natural log of x plus 1/2 times the natural log of 2x plus 1 minus 6 times the natural log of x squared plus 4. The idea is, by expanding the logarithm, we're taking products, quotients, and powers and turning them into sums, differences, and constant multiples, respectively, all three of which tend to be a little bit easier to differentiate. Next step that I'm going to do is implicitly differentiate both sides. And the implicit differentiation will be with respect to x. So on the left-hand side, I will be differentiating the natural log of y, and on the right-hand side, I will be differentiating 3 times the natural log of x plus 1/2 times the natural log of 2x plus 1 minus 6 times the natural log of x squared plus 4. Now, as far as the natural log of y is concerned, once again, this is implicitly defined. So derivative of the natural log function is 1 over whatever the input is, and the chain rule says multiply by the derivative of whatever said input was. For the rest of this, we'll be applying rules of the natural log as well as the chain rule wherever appropriate. 3 times the natural log of x will be 3 times 1 over x plus 1/2 times natural log of 2x plus 1 will become 1 over 2x plus 1 times the derivative of 2x plus 1. And finally 6 times 1 over x squared plus 4 times the derivative of x squared plus 4. That'll be 2x. At this point, there's a lot of algebraic simplification that can take place, and I will do so. We'll call this 3 over x plus, on the second term we can cancel the 1/2 with the 2, so this will be 1 over 2x plus 1, minus, we can take the 6 and the 2x and put them together in the numerator as 12x over x squared plus 4. Then, as is typical with implicit differentiation, we're going to solve for dy over dx. That step, the only thing that we'll need to do is multiply both sides by y. So y times the expression that we had just come up with. That was 3 over x plus 1 over 2x plus 1 minus 12x over x squared plus 4. And last step of the process is to substitute back what y is equal to. Reason being, if it's possible to have our final answer in terms of just x, that is what's recommended. So we're going to go all the way back to the beginning of the problem and say what was y actually equal to? Well, y was equal to this generous looking statement right here. Plugging that in for y will give us x cubed times the square root of 2x plus 1 divided by x squared plus 4 raised to the 6th power times the expression that we just came up with. There is a lot of algebra that could take place at this point. For example, you could distribute what y was equal to all 3 of these terms. You could try to get a common denominator and combine them all together. But me personally, I'm going to say, let's call it good.